Okay, thanks everybody for attending. I am going to get started here. I've got 10 o'clock Central Time, and to be polite in the interest of everybody else's time, I'm going to get started, and we'll have people joining us. In fact, I can still see attendees logging in as we speak. But I'm excited for this. It's not very often we get to do an advanced AB walls tutorial. We usually take that basic one, which was last month. Laura Horseman of our office took a bunch of you guys through the basic tutorial, and that'll cover probably 95% of the applications that most engineers out there get to see. But this tool that we use every day, AB walls, is very, very powerful, and these advanced features make it very possible to model site conditions and really kind of tell a tale of how a wall can provide a solution. And so again, this is something that if you didn't attend the basic tutorial last month, that's no big deal. We can go ahead and get you caught up at your time, at your convenience. You can just call in or schedule a tutorial with one of our engineers. My information will be at the end here, and you'll obviously get some follow-up response from me as far as help menus and stuff like that. But we're here as a resource. So the AB Walls Advanced Tutorial, if you look at this list, complex composite structures, trial wedge, all this stuff for seismic, and that's important as far as modeling slopes above the wall. But we're going to get into the wall drainage considerations, ultimate reinforcement. Then you get into some of the other ones like wall settings and advanced editing and terraced walls. All these things can be done, and we'll touch on some of these, but for the most part, I'm going to focus on the wall drainage. I'm also going to focus on internal compound stability and complex composite structures. And the whole goal is to build off of the basic tutorial of what was done last month. So with that, I'm going to minimize this and actually open up AB walls. And so every time you open up the program, what you get is a little ping that is sent to our website. And it just makes sure you're running the latest and the greatest version of the program. And so it's just important to understand that if there's an update available, go ahead and make that. Just go ahead, accept it. And then since I am going to be building off of last month's tutorial, I'm actually going to open up that file. So if I just go to the File pull-down menu on the top here and open, you're going to, I just saved it as my tutorial example, and it's just going to open up all the different files, and that includes the elevation view, the plan view, the cross sections, that kind of stuff. And I'm going to toggle through those again real quick just so you get an idea of what we did last month. And again, no big deal if you didn't see it. We'll be happy to catch you up. But test wall, no problem. If you remember, the way you navigate through the program are these arrows in the lower right-hand corner or left-hand corner. I'm just going to kind of toggle through those, and you'll see here's the elevation view. And with the elevation view, I got top wall, bottom wall, different colors in there represents kind of a different, the exposed and the buried block. And then if I move over to the next screen, this is the plan view. Since we did the plan view already and designed everything, you can see that the grid lengths behind the wall are also being depicted. This is the screen that was the panel, which you had all of the different cross sections being shown. And so since we've already designed them, the yellow lines representing the geogrid lines are being shown as well. Nice and neat, matching grids left and right, which is always a nice feature of this program. So you're looking at a total wall design, not as individual cross sections. And speaking of the cross sections, when I get into this next screen, I'm just going to go ahead and minimize this panel view by clicking on this icon up here. This is cross section number 1. And so this gives you the ability to do broken back slopes and surcharges and stuff like that. And I'm just going to go ahead and minimize and bring that back up so it's a little bit more detailed. But then you can toggle through the different cross sections, and because we did the full wall profile, you get a nice engineer's estimate too. So you get the total block counts, all that great stuff, which is good for bid comparison, submittals, that kind of stuff. But if I go back, so now we're going to get into the advanced features, and most of those center on this section screen. And in fact, what I'm going to do is kind of play around with section 0. So if you noticed in this upper left-hand corner, I had 6 sections for my tutorial example. I'm looking at section number 1, but you always have the ability to do what we call a section 0. And I got to admit, I use section 0 quite often, especially when one of you guys call and have a little question. Maybe you're working on an 8-foot high wall and have a little surcharge or something above. So I just toggle up using the slide bar right below section 0. I can toggle up, and maybe I've got that 13 course high wall, and being 8 feet, I want to bury a full block here. And so I'm just modifying that. But if I hit calculate, then you can see I've got an 8-foot high wall carried over some of the information that was in section 1 there with a 3-to-1 slope and a little broken back slope. So it's very simple to do a very quick cross section, and it makes it very easy to kind of provide some recommendations or answer a quick question as we go. And by the way, I should mention that if you have any questions, I realize everybody is in a listen-only mode. That's because we have a fantastic turnout for this. But if you have any questions, I am definitely checking the chat bar, and I'll try to respond to those as we go. And if you're having any technical difficulties, let me know as well. But you should all be able to hear me and see my screen, which was confirmed a little bit earlier before the session started. But so, for example, I like to play around with this thing. So you see I did have a little broken black slope. I had an 3-to-1 slope, and it went up for 2 feet before it leveled off, as you can kind of see here in the lower left-hand corner of the software. But maybe that surcharge starts above that. So we go a 250-pound surcharge, and then all of a sudden that's going to be like 6 feet back. And if I can do that and I hit calculate, now you can see that that puts that surcharge 6 feet back, and it's kind of towards the top of that hillside. And then I'm always checking my safety factors. So on the right-hand side here, I got my external sliding and overturning. Those need to be above 1.5 and 2 respectively, and as you can see, I'm above that. And then I also look at internal, and those are based on the grid layers, positioning, and lengths. So I got overstress, block pullout, and soil pullout. All of those need to be above 1.5, and as you can see, those look great. So the last step I do then is to calculate what we call compound stability, but I'm going to get into that here in just a little bit. Okay, so if you need to make any changes, maybe this is no slope or no surcharge, it's easy just to make those quick changes on the left-hand side and hit calculate, and it redoes everything for you. So now I'm looking at my standard design. So one of the things that we did back in 2014 when we were putting together our best practices initiative with the NCMA, kind of a zero wall failures initiative, we started looking at water, because we know water management is the key to any successful retaining wall project. In fact, most wall problems out there are because of improper water management. And ironically, the engineers, we've got a little bit of that blame to shoulder ourselves. We look at how much water is being diverted to the top of the wall, or maybe below grade sources weren't identified, or not even venting the toe drain out. So what we did is within the program, we brought in the whole water management section, and that is found in your design parameters. And we're going to kind of live in this little corner over here, because this design parameters, when I click on this, it launches another submenu. And I've got a lot of different options in here, and the big one kind of being this wall drain options. Okay, yeah, I am going to use the default values. I guess I hadn't moved that, so that the default soil values are at 30 degrees. So we'll just leave that as yes. But you can see we start with the wall drain options. We start right at the top. You know, we love being able to cap the top of this with some type of a clay material or topsoil or something of that nature, because it's important to divert that water around, even with the swale. And those are pretty simple. So I can just hit yes with the infill cap, and I can apply to all 6 sections if I wanted to, but I'm just doing section 0, so I'll just leave that as on. And if I hit hide and now I hit calculate, you can see, oh, I missed it. Let me try that again. So I've got wall drainage, I'm going to hit on and calculate. Now I've got that infill cap. So I missed it the first time, or maybe I toggled it off. I apologize. But now you can see that it's graphically being represented that we are topping the part of this wall with some type of impermeable layer. And that's important because what's now every cross section that's drawn will have this, or when you do your outputs, whether it's in the PDF format or in AutoCAD, it's going to represent this cap. And that holds true for maybe we've got that 3-to-1 slope again. So I got that 3-to-1 slope that goes up maybe 4 feet. And then we're going to go to design parameters, but we're going to bring in that drainage swale now. So we'll keep the cap on. We're also going to bring in our swale. And now when I hit calculate, I should have that 3-to-1 slope and that drainage swale. Again, being shown on every cross section as we go through. And it's just important. It calls it out. It's no longer just a line on paper saying swale. It is actually being represented in each cross section design too, so it makes it pretty easy. Right? So that above grade water is so important, and anytime you have a significant slope and a number of area or the site draining to behind this wall, you got to look at this water application or this water management here as we go through. So I'm going to go back to the design parameters, go to the wall drain options. I'm going to take those off. All right? And then we're going to get into the blanket and chimney drains. Now, the blanket and chimney drains, when are those used? It really depends on your site. Again, this is a tool that is used for designing segmental retaining walls, and every site is a little bit different, so we make sure we have the ability to model site conditions. But if you got tight soil conditions like that clay, or you've got a concentrated water source or some type of a spring or a seeping water, I definitely tell you the contractors when we do our contractor certification course that anytime we make a cut and we're digging our trench and we see water flowing, we got to stop. That design needs to be modified, and really what you're doing is providing a path of least resistance by using blanket and chimney drains. So the chimney drain is very simple. You've got a couple different options here. If I go to the chimney drain, I can say I want to go maybe 50% of the wall height, and we're going to keep it at 6 inches because this is using that rock. So if I keep that as on and I hit calculate, I now have a chimney drain that's being represented by the same color of the wall rock. So that clean, open grained material that's in the cores and 12 inches behind the stone is now being shown behind the mass as well. So if I wanted, I can leave that. I can go back to the design parameters, wall drain options, and now if I do a blanket drain, again 6 inches in depth, I can hide that, and if I hit calculate, now all of a sudden I have the blanket and chimney drain showing, tying in those heel and toe drain, kind of providing that path of least resistance. We know we've got a lot of producing partners and some industry experts out there that love using a geocomposite or some type of a geotextile at the back of the cut. Makes it easier for installation, makes it easy for that management of that material. And so that's pretty simple too. We brought that in based on different requests. So instead of the chimney drain, as soon as I click the composite drain, you'll notice that it automatically toggles the chimney drain for the rock off, so we're not going to use both. It doesn't matter. But again, if I keep that at 70, and then you can determine your on-site or on-center roll widths and stuff like that, that helps you with the estimates. So if you know what type of material is being spec'd out, which I hope you do, you can go ahead and make those changes. Then when I go ahead and calculate this one, now all of a sudden I've got the composite drain feeding into my blanket drain underneath. Okay? So it all is very positive when you're working through. Again, everything with the advantage of being shown on the cross-section is huge because now the contractor sees it over and over and over again that that's part of the design of that retaining wall. So let's go back to the design options again. And the last thing I want to show you, I'm going to turn off the composite and blanket drain, is this alternate drain detail. It's so important to show how this the toe drain and heel drains might be vented. Very often that gets overlooked. On commercial sites, maybe a little bit better. They might show where that drain might be vented or taken to some type of a stormwater collection system. But on most options, they're assuming they're going to come through the face of the wall. And if that's the case, very simply, you could save this as a default that every project you work on, you have this alternate drain detail. So we're going to keep this as on. Notice I got two options here. I got the wall rock, back of the wall rock or back of the infill. What is being shown here is the entire infill area where that's using that low permeable granular material at the base of the wall for the entire infill area. So what we're going to do is, I like it that way so it's consistent. We're just going to use the back of the infill, and now when I hit calculate here, it changes, so now you can see my cross section is representing that same alternate drain detail. So now the pipes have been raised up, they can be vented through the face of the wall. A couple different ways to do that. There's you can always cut the block in 4-inch square and put a T in the drain and come through the face. You got to be careful because we always like to put some type of a rodent screen or some type of a screen in there. A real slick option, if you want to write this down, is called Wall Drain Pro, and I'll include this in the follow-up email as well. I'm not endorsing it at all, but it does make it a lot easier to go ahead and drain that through. So instead of coming through the block itself, you're pinching this Wall Drain Pro. It's 1 3/8 inches wide, so you're pinching it between two units, and it's a nice, clean, simple look. But again, I'll provide some information on the follow-up email about it, just because it, especially with the rules that OSHA have passed about the silica dust generation, we've got to try to minimize how much cutting we're doing on a job site. This makes it really easy to do that. All right. So I just went through kind of the wall drain options. Are there any questions? Again, I didn't see anything in the chat menu, but if there are any, let me know, because I'm going to kind of zero this back out, and we're going to go on to internal compound stability, which is an integral part of doing the wall design. So again, if you have any questions, please fire them off in the chat menu, and we can go through that. But all I'm going to do is go ahead and go back to center here a little bit, just to keep things clean. I'm going to turn off the drain, alternate drain detail, and no slope. So I'm really pretty much back to my simple wall. 8 feet tall exposed, 5.5 foot of grid, which is all based on 60% of the wall height. 2-core spacing, which is all defaulted here. Again, being a design tool, you have the options as the engineer to go ahead and make those changes. So we'll leave this all here, but what internal compound stability is, this is the way we're checking the structure of the wall, kind of those bulging characteristics, making sure we've got full design considerations. So if I calculate internal compound stability, the first thing that pops up every time you run it during the design, it's not going to pop up every time, you'll see that, but it's going to be a gentle reminder. It's going to say, listen, this is not a global stability program. This is only looking at internal compound stability and not the entire hillside. And if I hit OK, it's going to run through some iterations. I don't expect to have any problems here, but I do want to pause and just kind of show you the wall envelope that we're looking at. You know, when we're doing the design, internal compound stability is only checking a certain portion of that area behind the wall. And if you look at it, it's defined here. It's twice the height of the wall, or if you're talking about slopes and longer grids, you might have the effective height plus the grid lengths. But a good rule of thumb is 2H. So in my case, I'm looking at 16 feet behind. Anything behind that is not really in my design envelope. And then you'll also notice that every slip arc is going from the leveling pad and bottom course up. It's not going underneath the wall. Again, this is not global stability. We're looking at how well this mass holds together by driving these slip arcs through this, now it's very similar, the Bishop method of slices, driving these slip arcs through the wall. So similar to a global analysis, but since we're limiting the entry and the exit points, it's only looking for that isolated bulge. But you can see, we define 20 points behind the wall as a starting option. We do 20 wedges. Again, you can, as an engineer and the designer, you can change those. Obviously, the larger, the more you go, the more iterations you have. Just on our little 8-foot high wall, we had over 70,000 iterations alone. And so then you can see the results. The results are done by course. So these are the lowest safety factor slip arcs for each course. I don't have a seismic load, so they're equal. So you can see everything for me is 2.3 or greater, which is great. I can get the sum of each load. Notice that if I walk across here, I got my pressure going for it and against it. Here's the shear strength. Here's the sliding of that soil. The grid capabilities or capacities, notice some of them are zeroed out, which is fine. It doesn't mean that the grid's not working. It just means that particular slip arc is not hitting that layer of geogrid. And we'll note that on that bottom layer one here where it's zeroed. And then geometry of that slip arcs too. So you get the radius and entry, exit points and that kind of stuff as we move on. But what I find cool is this pressure map. So what it does is it grabs your lowest safety factor and one of the higher ones, and I can draw a pressure map, and you can see that obviously the red and orange are the lower safety factor, but then you get into the bluer tints, and that's the higher safety factors. So you come in here, and as expected, you can see that those safety factors towards the bottom of the wall are more of that orange tint, and it obviously reduces as that you go up. And I want to point that out as a point of reference because we're going to go ahead and play around with this pressure map a little bit. So if I hide this, what you're seeing is the lowest safety factor slip arc for each course. Notice how, remember I said that first arc is not touching that layer of geogrid, so that's why you had zero contribution for that resistance. But everything's green, so we're in really good shape. No problems whatsoever. But maybe what we do, again, a site condition, maybe we have that 3-to-1 slope above the wall. So I've got that 3-to-1 slope. If I hit calculate here, you can see how that changes my design. Still 5.5 feet of grid worked okay. Safety factors are still being met in the lower, on the right-hand side here. Much closer now. I mean, I'm not failing by any means, but they did reduce because I have that surcharge above, or that slope above the wall. And again, I would still get in the habit of checking my safety factors for overstress, block pullout, soil pullout. None of those are highlighted or in red. They're all above the 1.5, so I'm okay. So the next step is to calculate internal compound stability. Now, the first thing that pops up is asks about, do you want to add grid to the slope? I'm going to go no in this particular case because what it's going to do is run the iterations with that slope above the wall. And now we've got another a pop-up talking about maybe global stability could be an issue. And why do we say that? Because more than 50% of the slip arcs are converging to that very last point. So what does that mean? Let me go ahead and hit OK and hide. Notice how all of the slip arcs, or at least the lowest safety factor slip arcs, are being shown and they're converging to this last point on top. Remember I was talking about the wall envelope. This wall envelope was twice the wall height, or the effective height plus the grid length. And so now all of a sudden we're looking at this, we've got twice this, and so I don't know what's beyond this point. Maybe there's a surcharge, maybe not. But because all of these minimum safety factor slip arcs converge, we just thought it'd be a really good idea that that it was that would be important. Shoal, you talked about an update. Yes, so last month maybe we were at the 1.8 for the software. Today there's a 1.9. We constantly are maybe updating. Sometimes the updates are nothing more than contact information has changed, block information has changed. Sometimes it's a design calculation was a tweak. But yeah, every time you open the program, you should be updated to the new update, and so yeah, just go ahead and use that. Okay, so I want to go back to the view internal compound stability, and I'm going to do that pressure map. And if I draw this pressure map now, I'm going to have a little bit different results. I still don't have anything below 1.3, which is the recommended safety factor, but notice that we have a lot more kind of orange in here, and even orange showing up on top, because that surcharge, that pressure is really being exerted at the top of the wall. I always find it interesting, so if I hide this, one of the site conditions we get quite often is people like to maximize their slope and minimize the wall, and we often joke because they think the blocks are, the wall is expensive, but in essence, when you're creating a heavy slope above the wall, for example, if I go to a 2-to-1 slope, and and I'm just going to back this down to 10 feet here a little bit, but if I go to 2-to-1 slope and I hit calculate, watch what happens. I go to 5.5 feet of grid, but now all of a sudden I'm at 6. And then if you really change it up, let's go to the design parameters here. If I use 27-degree soil, which is more of that clay material, and let's face it, we build we worked with a lot of clays. So if I hit hide here and now I hit calculate instead of 6, you really jump your grid lengths. Okay? Notice now that same 8-foot high wall in clay soils with that slope above, I need 9.5 foot of grid. So there are some instances, many instances in fact, that if you raise the height of the wall, reduce the slope above, you can in fact build a better structure and actually have less grid requirements too, because right now you're relying on this mass to hold up this entire hillside. And in fact, you get a couple other issues that show up when you calculate internal compound stability. Again, it's going to add a grid to the slope. I'm going to say no in this case. In my previous examples, I had problems. Section does not meet the minimum safety factor. And what does that mean? Well, if I go to my results here, it says I've got some safety factors that are below 1.3, and it's right at the top of the wall. In fact, if I draw my pressure map in this case, run through the iterations and map this one out, I have the orange all the way almost through this wall. Mine still hasn't completed yet, but I would suspect to see orange almost all the way through the wall, and then red even closer to the top where we're having those problems. Similar to what we saw with that 3-to-1 slope, but with that 2-to-1 slope, you just have more and more pressure exerted on that. Okay. Man, this is taking a little longer than it had in the past, but maybe the webinar is slowing things down. But notice how I've got orange all the way through, and then that red right at the top. So I need to do something about it. I can't let this isolated overturning, this is where we see walls start to bulge or overturn out. One way you can do this, remember I keep saying no, I view internal compound stability or calculate internal compound stability. I can add yes I can say yes to this, and now I can add a slope. So this is default values. It's going to start 1 foot above the wall, almost like a 2-core spacing at 1.3. I'm going to put 2 layers of geogrid in there, and the grid lengths, it's just grabbing that from what the minimum grid lengths were here, so they're consistent. So a contractor gets used to measuring out 9.5 feet. They can still use the 9.5 feet here. Now when I hit calculate, it's going to run through these iterations. And now I didn't have that pop-up. In fact, the results show no safety factor below 1.3 anymore. I'll try the pressure map. Maybe it'll draw a little faster this time. But now what that does is it brings in the grid into the slope. It disrupts those slip arcs, so now I don't have those same problems with the top of the wall overturning or bulging as we go through. And internal compound stability was something that was introduced a number of years ago. So it has been kind of commonplace out there where we're using internal ICS. So here's the pressure map of this. You can see no red lines, which is good. We actually got some blue lines showing up, so higher safety factors because of those slip arcs being disrupted. We've provided that stability of the slope. And here's what that kind of shows here now, where we've got that hillside being reinforced as well. So now we've got green all the way through. Okay, but internal compound stability is invaluable when you're looking at the total picture of that. In fact, if we tried to design a cross-section without doing internal compound stability, the software is going to flag it saying, hey, you haven't run internal. Is that something you want to do now, or are you going to come back and do it? It's commonplace. We're always looking at the external, we're looking at the internal, and now we're looking at this compound stability as part of the overall. Okay. Any questions for the internal compound stability in ICS before I move to this? Rich had a comment in the chat room. If you guys, it says minor correction to the PDF and printing, and so not sure what that means, Rich. I'll have to get back with you on that. But we look at how well that wall holds together, and all of this is outlined in our engineering manual as well, where we talk about internal compound stability. The water management is supported by the best practices, and then the next thing we're going to talk about is really complex composite structures. And before I do that, I mean, there's just different things that come up on a site. If you think about digging into a hillside and all of a sudden you got property line constraints, or you have utility easements, or very often you'll have a roadway above the wall that limits your excavation, or you want to limit your excavation or grid. So I can do grid underneath the roadway, or the new roadway, but then I don't want to have the grid in that subgrade or roadway structure at all for future maintenance. So you might shorten the grid or use alternate reinforcement at the top of the wall as opposed to the bottom. And what we did is we brought in, so let me kind of zero some of this stuff out of here again, just so we don't have everything. And I want to show you one thing here too. When I go to 0 and I hit calculate, it's going to use the same 9.5 foot it's going to show the same 9.5 foot. So I'm just going to go ahead and make that 60% of the wall height again. And now I'm back to my 5.5 feet here again. So everything looks just fine. I'm ready to go. But internal compound stability, if you want to know, or complex composite structures, we have a definition right here. And if you click on that, it takes you to a PDF document that is on our website. It's actually being supported in our engineering manual as well. And all that is, if I just zoom this in, it's a 12-page document that defines what complex structures are. So what we're doing is we have two different reinforcement options, whether that's two grid zones or maybe a grid and no fines within the same wall structure, and we're engineering those as one wall entity. Again, we talk about the design envelope. We're using internal compound stability to check to see if the wall will hold together, that mass. It just kind of paves the way for a lot of different options. So for example, the grid's shorter on top, or maybe no fines concrete at the bottom. You've got that easement or something, or utility that can't be disturbed. You can do a no fines concrete mass at the bottom, and I'll get more into that here shortly. And then what we do with the complex composite structures, or CCS, is the way we model this, and these are just some free body diagrams to help explain that, is we will look at the top portion of the wall by itself. And so the lateral earth pressures from the soil, any surcharges or dynamic loads, that's being modeled all the way through. Same thing with the top of wall. The bottom portion uses the entire hillside. Right? So we know that this is what, if we're looking at the entire wall height, this is what we're looking at for the lateral pressures, the dynamic loads, the surcharges. We've already shown how the top of wall is going to be modeled. The bottom of that uses the total height of that wall. So it's not like we're just looking at this height. We're taking the entire height of that mass and applying it. So it's relative. It's all, and it's accurate. So it's not individual. We're looking at it still as one mass structure. But what's kind of nice about it is it gives you some options. Anytime the top part, whether that extends further on, we're also checking a bearing capacity here, just to make sure we're not going to have any kind of a down drag force where this can't support that mass. So that's also being checked in CCS as well. But here are some different applications, where we have the top wall is a gravity wall, maybe a double wall. We've got no fines concrete being introduced. here. So we've got the grid different options here where you've got gravity wall and no fines on top, no fines on bottom, and I'm going to show you all of this back in the software. Okay. So CCS is one of those where we use it from time to time. In fact, we've had a couple designs where no fines concrete is at the bottom because of that pipe or utility easement, but then on the other side we've got a fence or something on top where we'll do a no fines concrete mass to help limit the excavation and maybe even provide some overturning resistance as well. And so the software is pretty good about this. When you look at the complex composite structures, one way to enter this real easy is by simply removing GeoGrid. If I go to Edit Spacing here, which is highlighted, and click on the layer of grid that has, or layer of coursing that has grid, it simply removes it. But now all of a sudden, I've got 4 courses that are unreinforced. And so this is going to be treated like a complex composite structure. And so you can see now instead of just one sliding and overturning value, I've got a lower and an upper values. So the lower structure sliding and overturning, upper structure sliding and overturning. Obviously not much there at all, no concerns. So we could treat this as a gravity wall. Notice though, I no longer have, and you can see this bright red, that the overstress, block pullout, soil pullout, those values do not apply for compound composite structures. We are relying on internal compound stability to check. So I would just run this analysis real quick to make sure I'm not having any problems. So I go ahead and hide this, and technically I'm looking at a structure now that has a gravity wall on top and then a reinforced structure below. All safety factors are being met, so we could make a judgment that this could work just fine. You know, if I try to do another layer of GeoGrid, again, spacing is highlighted. I click on that course that has grid. Now all of a sudden, I've got, 6 courses that are unreinforced. I've got my upper and lower structures. Lower structure looks great, but now I've got problems with my upper structure. I can't have 6 courses of grid or 6 courses of block without some type of reinforcement. Well, if I want to double my wall up, so for example, if I use this double block feature, and so here I just start clicking on the courses, notice I'm doubling the thickness. So in this case, I would flip the block end for end, and so it would match the setback, or if you're using the field stone, you could use a longer anchoring unit. But I haven't made enough of a change yet, so I need to keep adding to my blocks until I get my entire gravity wall calculated. So now I have all 6 courses as a double wall. Notice how it changed my safety factor now to being it'll satisfy this. So now my overturning is above is 2.4. So I could look at this as a reinforced structure with grid, and then a double wall gravity wall being 2 feet thick to be to support the upper wall structure. Again, you should always double check internal compound stability as you go. I'm gonna forego that as I keep playing around with this. So instead of a double wall feature, what you can also do is we call the no fines concrete. And so I'm going to unlock this, calculate it so it goes back to standard, because this is one way to get back to just as if you calculate a section for the first time. I go to a no fines concrete gravity wall, and I click on the course, and it tells me, do I want no fines concrete on top or bottom? I'm going to go top, and let's try that 2-foot mass. I hit hide, and let's hit, you can see they got 2 feet, so in essence it's the same thing as using that double wall, and now all of a sudden I've got my GeoGrid on the bottom and then my no fines concrete on top. And so a great way, again, you would calculate internal compound stability. I know we've used this on countless applications. One of them I outlined already, where a new roadway is coming in. They don't mind the grid down below, but as soon as they have their curb gutter, that kind of stuff, they don't want anything protruding into this. So we've just gone into a no fines concrete on top to get around some of these options. Okay. We've also talked about making sure we can do a little bit of both. So we can do 2 grids. So if I go into the calculate feature here, reset it, so instead of using the grid here, I'm going to shorten grid lengths, and you're going to see this. So I go to edit length here, and now I go to the top of wall, and maybe we try to make those 4 feet. So I don't need to make a huge change, but now you can see internal compound stability, or internal for soil pullout, is being triggered here. I've got a problem with the mass, but what I'm going to do is shorten another layer of grid and allow this to be analyzed as a complex composite structure. So I have to come in here, check that, make that 4 feet, and now all of a sudden it's looking at these as 2 structures again, checking my internal or external for sliding and overturning, and then without a doubt I would make sure I have my safety factors for internal compound stability. Okay. I just had a pop-up on somebody said that their screen was frozen. Is everybody still able to see my screen? I just want to make sure I got confirmation that it's not a global issue and not one at a time. Okay, great. William, I appreciate that. You never know, especially when you're listen only. I feel like I'm talking to a closet here. So you guys, thank you for that. I'm going to continue on. And whoever has that problem, just maybe call into the engineering department when you get a chance, and we'll take you through any part that was missed too. So, okay. So I showed you the grid top and bottom, the top part. I want to show you how you can kind of change the bottom portion here a little bit, because there's some little nuances here. So again, I'm going to unlock this and calculate it, go back to kind of that 0 section. Now I'm going to try to shorten that bottom layer of grid. Okay. So again, grid length is here. I'm just going to scroll down, and let's say I go to number 1. I'll make that 4 feet. I hit OK. No errors on this one, but now if I go to here and I make that 4 feet, again, make that as a complex composite structure, I hit OK, you're going to get a note that pops up. Because what you're trying to do is go less than 60% of the overall height. And that is not what we want to do. If you ever have these conditions, these are more of a hand calculation. We've got MathCAD software or MathCAD spreadsheets that can help you. Let us be part of that, but we don't want to just go in and shorten the bottom layers of GeoGrid to less than 60% of the overall wall height. So you'll see that it didn't let me do that. In fact, if it does, it's giving me errors. It's giving me grids are less than 60%. It's giving you, and this can't be removed. It's going to be printed out on your sheet. So I'm going to go back, make these 5.5, and hit calculate again. So I'm back to the standard, and that holds true for no fines concrete as well. There's a limitation to no fines concrete. If I go to no fines concrete gravity again, that's how I transition to that complex composite structure, and let's just say the bottom portion of that wall, maybe from 6 courses under. So now I go no fines concrete bottom, and we try to go, let's go 3 feet. I hit hide here. It's going to tell me the lower structure needs to be increased for that minimum input value. And I'll show you where that alternate reinforcement, how that comes into play. So I hit OK. It's going to give me that result. And notice that 3 feet didn't work. It had to be 3.8 feet at a minimum based on that 60% rule. And where that's coming into play, in fact, we got it at 70%. You go to the design parameters. This is where that alternate reinforcement comes into play, these design options here. No fines concrete, if you ever just want to do a simple design, and we will here shortly, but notice this tab right here, or this section, complex composite structure ratio. Minimum bottom needs to be at least 50%. Okay? Top default ratio is 70%. So you have some control over this. You can change the ratio, but notice that 50% rule is kind of grayed out. That's part of that. So I can't go less than 50% without making some modifications through some hand calculations. But if I wanted to do all no fines concrete, I can come in here and come to my design options like I did before, and I hit design with no fines concrete as yes. You can see the default comes in at 40% because I'm using that as an entire mass. I hit that as hide and I hit calculate. Now I've got a no fines concrete mass. I know I can't go less, but let's say I wanted to go taller on top. I can click here, click on which course I wanted to stop. I got 5 feet high. Now all of a sudden I got 2. No fines. Oh, it must have been on the bottom instead of the top. But either way, you can kind of catch what I'm doing. I can change my mass to go longer, but I can't go less than that 3.5 feet. And again, everything needs to be checked with internal compound stability. So if I click on that, I'm going to make sure my mass holds together just fine. And I've got all these slip arcs. They're all green, and you can see I got a safety factor of 3.2, almost 3.3. So internal compound stability works well all the way through. So, I have I've been talking for about 45 minutes. I've gone through the internal compound stability. I've gone through complex composite structures, and I started with the wall drainage considerations. Are there any questions? And I'm going to pause here a little bit. I'll give you guys a little bit of a chance to enter anything in the chat room, and I'll be happy to answer any questions as we wrap this thing up. Okay, it's pretty blank. I had had a few guys keep responding that they can see the screen. I had a couple guys say it happened to me that they had to reload or refresh. But I tell you what, guys, I know I went through 3 pretty big topics right away. I hope I made it look easy because I know the software in and out. But the best thing you have is you've got a resource. You've got the ability to send the engineering department an email or give us a call at any point. We've got a network of engineers here that are second to none. We're all intimately familiar with this program and would love to do nothing more than to help you solve your problem. And we love the challenging ones. You know, if you've got a unique application, you can send us a little bit of that site plan and maybe even your AB Walls file, and we'd be happy to do that. So I do have a question here talking about been updated to account for the horizontal loading. Boy, that's a great question. We've kicked that around here a little bit. So what the question was about horizontal loading from maybe a fence on top of that wall. We have not, as of right now. We've been talking about it for years, to be perfectly honest, but we've got, again, hand calculations, or we call it that MathCAD spreadsheet that we use. Gives us a little bit of flexibility as far as post spacing and things like that. So we did not include it in the software, but we do have tools available. Again, just send us an email. We'll be happy to help where we can do that horizontal loading from a wind fence or even a traffic barrier. Obviously, those get a little bit more substantial. But there are tools available through Allan Block here that can help you with that, but it's not in the program as of right now. And I'm not saying it will be anytime soon because it seems like that's a line that we just don't want to cross. We want people to consciously design that top wall condition out there too. So I guess if there's no other questions, what I'm going to do is just kind of wrap up. I do have a question. Multiple tiered walls. Thank you. I missed that one. What we do, let me go back to AB Walls, unlock this. What we do for terraced walls, I'm going to design with GeoGrid, sorry. We model that terraced wall as an additional surcharge. So it doesn't do terraced wall applications per se because remember this is not a global stability program. What we do is we look at each wall individually. So if I had maybe a 4-foot high wall that was 6 feet back, I would model that as just take the 4 feet times your unit weight of soil. If I assume that was going to be 120 pounds per cubic feet, I would in essence have 480 pounds of dead load 6 feet back. And when I calculate that, that puts that additional weight on top of that wall. Okay, so we have the ability to model what a terraced wall will do to another wall, but we don't look at it as an entire structure. That's where global stability really comes into play too. So we can model terraced walls with the flexibility of our surcharge applications, but terraced walls, that's a kind of a, I wouldn't say a red flag, but for us that's a key indication that global stability should be analyzed. But great question, Kevin. I appreciate that. If there are any other questions, keep them coming. But I'll just wrap up here. We've talked about kind of the design options with the water management. We've talked about what factors or influence complex composite structures. What I'm going to do is send you guys a follow-up email. It'll have maybe some information about that Wall Drain Pro, maybe even some sleeve-it information about top wall overturning with that fences, based on Cheetah's question there about that horizontal load. One slick way of preventing that is putting in a little cantilever footing from a sleeve-it system for that fence loading. And then also the evaluation. So if you are interested in receiving continuing education credits, part of that email will have a form on it. Just go ahead and complete that form, email it back to me, and we'll be happy to issue a continuing education units for your hour of time here. But if you, without anything, like I said, we are here to help. My contact information along with the engineering department will be on that follow-up email. We're here, always here as a resource. I know we get to do retaining walls every day. That is not something you guys tend to do. So tend to lean on us with our experience. We're happy to impart any knowledge that we have as we move forward. Any other questions? Okay, let's see. William, you said IBC has changed the requirements to not require calculations for retaining walls 4 feet high or less. This is dangerous. You're exactly right. I could not agree more with you. I always get a little nervous when everybody says, when do you need to engineer a retaining wall? Well, I mean, you can go to this here, and I can make a 3 foot high wall, and I put that surcharge right on top of it, and you're going to see that it's going to have to be engineered. If they don't think I can do it as a gravity wall, because a lot of people think no engineering means no geogrid, I do not even a 3 foot high wall with a surcharge, and all of a sudden I've got safety factors that are of a concern. So I couldn't agree more with you. Just because it doesn't need to be engineered doesn't mean it doesn't need to be reinforced. So that IBC change of 4 feet is dangerous. That's where education really needs to come into play. This is where we have our contractor certification class. Every year we are training thousands of contractors to make sure they are qualified to install the designs that you guys are putting out. And we touch on that subject right away, making sure they understand the limitations of what the systems can do and the fact that you have to go through that. Let's see. Does AB have a representative code council bringing discussions? Sure. We participate in the numerous organizations, NCMA being one of them, and NCMA is very active in the code council trying to make sure we have these addressed. As you guys all are aware, I tell you what, there are things that are slow moving, and anytime you're talking about code councils and changing codes, that is not easy. So once it's in, it's even harder to get out, but that is something we will continue to work on as we go through the education process. Chad, you talked about able to do multiple stepped surcharges, say 4 foot out, 100 feet, and then 4 foot to 8 feet is 200. Yeah, you bet. Again, if I come back, I'm going to just go give it a little bit of height, no problem. I calculate this. Oh, I better use actually grid on this one, sorry. I calculate this. Let's say I've got, you said 100 feet here.
I would model the first one this way. So you said first 4 feet would be 100 feet. The rest would be 200. I would make this 200. I would start that 8 feet back. I would use a line load, that'd be my 100, start that right on top of the wall, and that at 4 feet. And now I have the ability to change 2 different surcharges. And what did I do? Oh, I started make this 8 feet. So you make this 4 feet here. So now you have the ability to do 2 different surcharges, 2 different types, and using the combination of line and dead loads. But yeah, that's something we do quite often, especially when you're talking about parking lots and sidewalks or anything like that, or a strip load from a building. Like I said, this software is a very powerful tool. There are many features in there that we covered today, but much more that we did not. Anything that comes up, just go ahead and give us a call. Chelsea, you mentioned what is the reasoning for using 2 for the OT safety factor rather than 1.5? Are you just conservatively using that? Overturning, when you talk about gravity walls, the NCMA and the industry, you can go down to 2 or 1.5. But for reinforced walls, the industry does recommend a safety factor of 2.0. You have the ability to make that change. Any of our safety factors in here, as far as are just recommendations, we default to 2.0 because that's what the industry recommends. But if I'm truly doing that gravity wall, if I come back to that low wall, 3 feet, maybe no surcharges, right? And I want to calculate that without grid, I can use that and check to see if that works with a 1.5 sliding. And in this case, 2.0 for overturning would have been fine as well. But I can always double check that. Okay. Do you do the different surcharges correctly in this example? I'm not sure where that question is from Allan. Talking about I did do multiple step surcharges, say 4 feet out I did the 100, and then 4 to 8 feet I did the 200. So you had both 4 feet. Well, let me go back. Like I said, I like 0 section for many reasons. I can always go 200, 4 feet start, 100, starting right at the wall, ending at 4 feet. So it's ending, this one's starting. I hit calculate, so I'm pretty sure I had this right the first time, where the first 100 or first 4 feet was 100 pounds per square foot, and then it transitions from 4 feet beyond doing my 200. Okay. Okay, we got lots of questions. I like this, but I tell you what, we're at an hour now. I can take a few more questions here, but other than that, I'm going to sign off and we'll get started. But I see somebody is typing now, so let me just answer 1 or 2 more questions here and then we'll get going. Okay. I think whoever was typing decided to change their mind. So, all right, guys, I appreciate your time. Once again, if you need a copy of the software, send us an email at engineering@allanblock.com. If you have a version of the software and just want a refresher on everything, give us a call. We're happy to do that, but let us know how we can be a solution to your next project. If there's anything we can do for you, just let us know. You guys will get an email from me here yet this week. Thanks for attending, and we'll look forward to the next time.